Hello, welcome to another Stat 510 video. So what I'm going to do in this video is go over a couple of the likelihood ratio test questions from uh, a previous homework. I guess it was homework 8 where I already released solutions for a couple of reasons. One is because that was content from the week where I did not create my own videos and we used some external ones that folks weren't as happy with. So this is kind of serve as a supplement to that. Also, because I'll just say it in this video, you can guarantee that there will be a question on the final exam about a likelihood ratio test. So this will, me walking through some of these problems, I'll maybe highlight some things that could potentially be helpful there. Another thing, if you're watching this video, is as I'm doing these videos, I'm also thinking ahead to the final weeks of the class. And I realized in sort of making the week in which you're watching this a review type week, there was already a review type week scheduled. Long story short, scheduling this semester, I keep screwing up because without the spring break, the number of weeks is different and I keep forgetting. Anyway, I'm going to say some things about that announcement. But what I want to say about this is I think this is an example of a type of video that I'm going to do the rest of the semester. So I kind of don't want to do any new content. What I want to do is go back to old content and especially like old homework questions, do videos of me, maybe not, I mean, potentially doing the whole problem or like doing parts of the problem and explaining. So I'm probably going to make a Piazza post that says, hey, is there a topic or a particular homework problem that you want me to talk about again? And I'll maybe do some more, instead of proactive content, I'll do reactive content to get you sort of exactly the things that you want to talk about. Okay, so yeah, let's have a look. So I believe this was one of the homework questions. So we have the situation where x is a binomial random variable. In this setup, this n here is going to be known because we're going to do it for a known sample size, but p is unknown. I should say that this would be equivalent in final result to instead of x being binomial n comma p, we could have x1 through xn that are Bernoulli p. That wouldn't change the final answer, although it would sort of affect the intermediate likelihoods, which we'll see in a second, but ultimately they would produce the same result. So that might have been a confusion about this because it looks like one observation, but really it's kind of n observations grouped as one because that is kind of what a binomial is. Okay, so we want to develop the likelihood ratio test in this situation. So ultimately what we want to do is we want to maximize the likelihood under the two hypotheses. So ultimately, in this class, we're really only considering simple nulls, or I should say point nulls, which is what we have here. So that makes our life pretty easy. So really all we have to do is maximize the likelihood under the alternative. Realistically, there's actually a note about this in the book. We're not doing it over the alternative. We're doing it over all possible values of the parameter. So realistically, what we're doing when we say get the maximum likelihood under the alternative, we're just saying get the maximum likelihood. So in this case, we don't really need to go through that derivation because we've done it before. It's very well known. It's just x over n. This is the MLE, or in this case, in particular, it's the MLE under the alternative, right? Okay, so the next thing we need to do is write down the two likelihoods with those values plugged in. So the likelihood for what we'll call P0 here is, what would that be? So that would be n choose x, p sub 0 to the x, and then 1 minus p sub 0 to the n minus x. If you reworked this problem to be n Bernoullis, you would have just this part here. But we'll see in a second how that wouldn't matter. Okay, so the likelihood with that alternative MLE plugged in would be something like this. So that's p hat to the x, 1 minus p hat to the n minus x. Okay, so, and again, this is this is for the null, and this is for the alternative. Right. Okay, so the next step would be to calculate the likelihood ratio. Well, I'm just going to say that, and I'm going to re-explain that in a second because there is one minor confusion there. So the likelihood ratio is the ratio of the likelihood under the alternative to the null. Now, I should say that that's actually an arbitrary choice. Some textbooks, some references, you'll see it as null divided by alternative. That actually really messed me up in writing up the solutions to one of these problems, and there's a whole exchange on Piazza about that, but I digress. But so in this case, we're just dividing these two things here. So you'll notice that n choose x will go away, and that's why it doesn't matter if you do Bernoulli or binomial in this case. But so in doing this and a little bit of algebra, I would group it together kind of like this. This to the x, and then 1 minus p hat over 1 minus p0, all to the n minus x. Okay, so now, importantly, we would reject the null when this thing is large. And what is large depends on the distribution of this thing. So what we really want, say for an level alpha test, is we would want to reject this for the values of this statistic that account for the 5% of the largest possible values, right? But in general, that's difficult to do because I don't know about you, but I don't want to develop the distribution of that statistic. Someone probably can. I don't want to do it. So what we've often looked at then is something called the likelihood ratio statistic, or at least that's what the book calls it. So for the likelihood ratio, which is literally just the ratio of the likelihoods, I'm using capital lambda. But for the likelihood ratio statistic as defined in Wasserman, I'm using lowercase lambda, which is defined to be 2 times the log of the likelihood ratio. So that's a little confusing because some people will just call that the likelihood ratio. Some people will call the likelihood ratio the likelihood ratio. Again, we're bad at naming things in this field. But anyway, in this case, that works out to be something like, in my notes, I'm missing something. So this should be 2x log of p hat over p0 plus 2 times n minus x log of that thing, right? So now we can calculate this statistic, right? For a particular data set, we can get the value of this. But now we have a little bit of extra information, which is for large samples. We could say that lambda has an approximate chi-square distribution with, in this case, 1 degree of freedom. So sort of in the same way that we can use the central limit theorem to sort of approximate probabilities, even though it's an asymptotic result, like obviously we're not going to have an infinite sample size, we can do the same thing here. So with that, we can get an approximate p-value, which would be, in this case, the probability that a chi-square distribution with 1 degree of freedom takes a value larger than that chi-square statistic that we found. Okay, that's not doing the whole problem, but that's the important bits. I forget what extra stuff we asked you to do in the problem itself, but those are the important bits. Now, I want to do another problem because I think that this is somewhat intuitive, the fact that we would reject when the likelihood ratio is large, because that means, well, the likelihood of the alternative is so much bigger than the null, and then so that kind of fits better. But I want to do another example where I think when we just look at the statistic and don't even consider this notion of likelihood, it'll reinforce that idea to us. Okay, let's do that in a second. I'm going to pause for a second. I realize it's silly to tell you that I'm going to pause because you don't see the pause part, but you just hear me coming back talking about it like I am right now. Anyway, all right, so I think this was one of the trickier problems on whichever homework we're talking about. I think it's homework 8. So in this case, we have x1 through xn that are sampled or assumed to be sampled from a normal distribution, and the intention of the problem was to say that both of these are unknown. And whether or not that was clear in the problem, I apologize, but that was the intention. Okay, so, and then we want to develop the likelihood ratio test for these two hypotheses we have here, some simple point null versus the alternative of all other values, right? So what we could do is we could say, well, the parameter for the alternative is mu sub 0 comma sigma squared sub 0. And similarly for the null, for the alternative, we would have mu sub, let's call it 1 comma sigma squared 1. Now, the thing is though, of these two parameters, well, sorry, let's call it 4 parameters, right? So mu 0, sigma squared 0, mu 1, sigma squared 1, only 3 of them actually need to be estimated. Because as part of the test, we're assuming a value of mu sub 0. So that in the case of this test, we're assuming it's known to be some value mu sub 0 that will be specified in the test. Okay, so we need to go about estimating all of these things, right? So I'm not going to go through the steps to do it, but you should, to verify that you get this result. Under the alternative, under the null, the estimator for sigma squared sub 0 is something like this. Okay, that is for the null. And then for the alternative, it's the usual MLE estimates for a normal with 2 unknowns. If you haven't done so, it wouldn't hurt to go through that exercise, but you should make sure you come up with these results. But these are sort of well-known results that we can just sort of assume that we all agree with. So again, this is the MLE that is under the alternative. So in the end, what we have here is theta 0 hat is mu 0 comma this estimate, and then for the alternative, call it mu hat 1 comma sigma squared hat 1. Okay, cool. All right, well now we need to write down the likelihoods and plug in these values. So what I have here is just a generic likelihood given some theta where theta is the vector mu comma sigma squared, right? So this is just your standard likelihood for a normal distribution. I'm now realizing that I'm gonna have to write a bunch of stuff, so bear with me. So first, the likelihood under the alternative, I should have pre-written this part. So this is simply plugging in the estimates that we got here. So what that would be is, so basically putting hats on things, more or less. Right, we're doing alternative, so it's like this. Then 1 minus 2 over, we need to put a hat here. Then xi minus x bar. How did I write it in my notes? Yeah, we'll do x bar, which is mu 1 hat. Okay. All right, and then we can do the same thing for the null, which again mostly amounts to putting hats on things and putting the 0 subscripts for the relevant estimator, except now the difference will be minus 1 over 2 sigma hat squared 1. Then here's where the difference comes in. We still have a mu 0 here, because again, that's, for the purposes of this test, we're assuming that's known. Okay, so then what we want to do is look at the likelihood ratio, which is the ratio of the likelihood when you plug in the estimates under the alternative divided by the likelihood when you plug in the estimates under the null. Now, before I do that, I want to go back up to those two expressions, and we're going to wave the magic algebra wand and see a bit of a simplification here. So this works out to be n e to the minus 1 all over 2 pi, and then this usual sum of squares looking thing, and that all to the n over 2 power, I believe. And then similarly down here we have n e to the minus 1 all over 2 pi, and then a sum of squares looking thing like that, and over 2. Okay, so now dividing these two things becomes a whole lot easier, and we end up with something like this. I'm dropping the I equals 1 to n indices just because I'm being lazy, but we all know it's really there. Okay, so I want to pause here. Actually, kind of want to end here, but a lot of explanation still. Okay, so the problem would have carried on at this point, and you would, I think I asked for, like, you know, what's the limiting distribution? Maybe I had you get a p-value, I forget. But importantly, I had you compare this to the Wald test. And I have like a page of derivation showing that they work out to be equivalent. I'm not going to go through that here, and I will put you at ease right now. You're not going to be asked any questions like that on the final. That's more to sort of just be like, FYI, hey, look, these things are the same. Here's how we would show it, kind of thing. But I'm not going to ask you to reproduce that. But so thinking about the intuition here a little bit. So we mentioned that ultimately we want to reject this ratio, this statistic, when it's large. And I said that there's already some intuition about that based on, you know, just thinking about, well, we want the likelihood for the alternative to be big compared to the null, and that's when we reject. And that hopefully is somewhat intuitive. But I believe that this statistic that we're looking at here is also very easy to understand. I don't like using easy. It's hopefully illustrative, right? So ignoring the raised to the n over 2 power, because we sort of don't control that, n is the sample size, whatever. Let's now look at the numerator and denominator here, which I'm going to refer to as top and bottom so as to not confuse myself. So the top here, basically what it's saying is how far away are each of the data points from the hypothesized value of the mean, and looking at that like a squared sort of sum, you know, the distance kind of metric, right? So basically, this is going to be small exactly when, you know, the data points are sort of as close to the mean as possible in some sort of square distance sense. Whereas the bottom here, same thing, but now instead of the assumed mean, it's the estimated mean, right? So how close are all the data points to the estimated mean, right? So another thing to point out here is that, and this might help in general, is that the bottom is going to be either equal to or smaller than the top, because the bottom can take, so x bar could, in very rare cases, be mu sub 0, and then they'd be exactly the same. But because of the MLE and the way the normal MLE works, this x bar has the potential to make it smaller, and it can only be smaller or the same size. It cannot be bigger. But so if you think about this, well, if the alternative is much better than the null, that means the bottom here is going to be much smaller than the top. And then when you do that division, this becomes a very large statistic, and that's when we would reject. So hopefully that adds a little bit of intuition into why we reject the likelihood ratio when it is large. Again, we're not going through the business of actually doing that and maybe appealing to the asymptotic distribution, but I just wanted to touch on that intuition about, you know, why it is that this actually is a thing we would want to do, and that it makes any sort of sense. Okay, so that's it for this video. I haven't said my line yet, but I will. But I wanted to just say again, if this style of video is helpful, which I really hope it is, I'd like to open up for some discussion on Piazza, and I'll maybe start a post at some point before I post this video to say like, hey, in the next couple weeks leading up to the exam, which problems would you like me to see? Which problems would you like seen done in a video style like this? Obviously, I'm not going to do every single homework problem we've ever done, and I won't fulfill every request necessarily, but I will use that information if if a bunch of people say like, oh, this problem and it really sticks out, well, then we're going to make a video about that. This is the kind of thing we normally do in office hours in a less formalized way, but not everyone can come to all the same office hours, and I don't want to run a live session because we are literally a global class, and we have a lot of time zones represented here, so I wouldn't want to do that. But so I think this is a way that we can have some interactivity where you say, well, I need help with this type of problem. Here's an example of one that I struggled with, and then I can do an explanation type video like this. So maybe go back and look at some of the homeworks and think about that. A reminder, if you haven't been looking, I have been posting solutions on Compass for all these homeworks, and thanks to the folks that have pointed out a few typos in those. I should mention that if you've been saving those files along the way, it might be a good idea before the exam to just download the most recent version of them. There's not very many typos, and often I change them so fast that I'm guessing people haven't downloaded it, but just do be aware that a couple things here and there have changed, but that's not like a huge recurring issue. Okay, so time to stop rambling. So as always, if you made it to the end of the video, good job, and I will see you in the next one, which will hopefully be a reaction to your comments to what problems you'd like to see done. Okay, that's it.